Hi everyone, I'm Thomas Longden. I'll be talking today on blue and green hydrogen and how it fares under zero emissions objectives. This is work that I've been doing with colleagues at the Australian National University here in Canberra, Fiona J. Beck and Frank Yotso pictured next to me. Before I begin, let me just remove the video and give myself more space for the slides. And you'll see that my email address and Twitter handle are pasted below in case anyone wants to get into direct contact with me. So why are we talking about emissions and a new hydrogen industry? Well, there is a lot of discussion about the emergence of a new hydrogen industry, but we raise the question of whether it will actually help decarbonize energy systems. Many countries have developed national hydrogen strategies, but key countries, including Australia, do not have mechanisms to ensure that that hydrogen industry will lead to low emissions. Germany is a notable exception in its insistence on green hydrogen and only seeing a future for green hydrogen. But it's important to note that potential importers such as Japan and South Korea have little incentive to demand green hydrogen, which is hydrogen made by electrolysis using renewable electricity. The imported hydrogen will be accounted as zero emissions, even if its production is emissions intensive in those supplier countries. How they use the hydrogen will actually be clean, no matter how the hydrogen was produced. So the emissions of the production of hydrogen will be accounted for in the supplier countries, and that includes Australia having a strategy and a vision towards being a hydrogen exporter. But those countries will typically put the establishment of a new export industry ahead of achieving low national emissions outcomes. So low carbon hydrogen can be produced using a range of technologies. Green hydrogen, as mentioned, is electrolysis and renewable electricity. Blue hydrogen is produced using steam, methane reforming, and gas, using carbon capture and storage to reduce the emissions profile so that it's low carbon. Many recent studies and strategies have compared technologies, but have not assessed the effects of lower than perfect CCS capture rates. And so while blue hydrogen, so SMR, is producing cheaper hydrogen now, green hydrogen is likely to improve its cost competitiveness over time. And tightening carbon constraints may lead to a case where blue hydrogen production assets could become stranded in the future. So let's talk about the Australian hydrogen strategy as an example. So this is the emissions intensity of production presented in the Australian hydrogen strategy, and the same numbers appear in the roadmap. These have 90 to 95% capture rates for coal gasification and SMR with CCS. There's no mention of less than these best capture rates, at least not directly. So why worry about emissions intensity? Well, high capture rates are expensive, and private firms will not aim for high capture rates without a reason to do so. And the term low carbon or clean should not be used for all CCS options, as you'll see with this analysis that we've done. So the term clean hydrogen is used in the Australian hydrogen strategy. It's applied to both clean renewable hydrogen and clean CCS hydrogen. So CCS hydrogen here is described as a case where emissions are captured at a high level and permanently stored, but it's not clear from the strategy what that high level is and should be. Of course, the best capture rates are 90 and 95% in that report. But without it being specified in the strategy or certification scheme, it's unclear who will choose what is high and what is not. As you can see here, there's a range of Australian government reports. The three examples here all use the term clean hydrogen, and that includes the National Hydrogen Roadmap that's been developed by the Commonwealth Science and Industrial Research Organisation, the Hydrogen Strategy, and the New Technology Investment Roadmap, which is at the discussion paper stage. A notable comparison for those reports is the German National Hydrogen Strategy, which states that the federal government only views green hydrogen as being sustainable in the long term. On the extra article presented there is an article that we wrote in the conversation for a general audience, and we point out that for hydrogen to be truly clean, it must be made with renewables and not coal, and this work is an extension of that analysis. So what do we do in this paper? We compare SMR with CCS options for different capture rates between 52% and 89%. Our analysis shows that emissions intensity will be high when lower CO2 capture rates are used, and that 4 out of the 5 SMR with CCS options are not low carbon, and that is based on the CertifHy hydrogen certification scheme that's been proposed and a low carbon threshold in that proposal, and including fugitive emissions. So why is this a concern? Well, capture rates at 90% are much more expensive than other lower capture rates. And SMR with CCS, both technologies have long lifetimes, which means that they may become uncompetitive with electrolysis, and it's not clear whether CCS can be deployed quickly enough to capture notable emissions before 2030. So here we compare estimates for the levelized cost of hydrogen with different rates of CO2 avoided. A key reference that we use throughout the paper is the IEA GHG report from 2017, which has a base case SMR facility and 5 different SMR with CCS options with capture rates from 52% to 89%. And you can see that the highest capture rate of 90% happens with a hydrogen cost that's above $2. The CIRO report and the IEA G20 report prepared at the request of Japan has much lower hydrogen costs with 92% capture rates. So let's put that in graphical form. So there you can see the blue dots have the IEA GHG estimates going from just under $1.50 with no capture, with just a basic SMR facility, and then past $2 for a capture rate of 90%. We're not sure why the IEA report goes from $1 to $1.50. That seems to have been a shift based on assumptions of technological improvements that aren't reflected in the IEA GHG report. And also the CIRO numbers there you can see are notably cheaper than the IEA GHG estimates at a very similar capture rate, actually a higher capture rate of 92%. So just changing slides. Oh, sorry. So here we've basically used the emissions from the IEA GHG report, the process emissions for each of the technology options presented, and added fugitive emissions to those technologies based on the amount of gas that's used during the process. And so you'll see that that actually changes. It's not clear on the graphic, but it does actually increase for the 89% capture rate case where more gas is used to be able to capture more CO2. So we compare the base case to the other technological options with CCS applied, and the CertifHy low carbon threshold is a 70% improvement based on the SMR base case. And note that in different documentations, it's either a 60% or a 70% improvement. In this case, we've used a 70% improvement. Nevertheless, you can see that 4 out of the 5 SMR options would not be classified as low carbon based on the CertifHy low carbon threshold. So we asked the question whether SMR facilities could become stranded assets. And the key drivers of the levelized cost from an SMR facility are the lifetime of the plant, which is usually assumed to be 25 years, so quite long, and the amount of CO2 captured. So SMR could become a stranded asset if there's a breakthrough in the cost of producing hydrogen using PEM electrolyzers, or a shift in public attitudes or a global imperative to move to zero emission energy systems. We reflect that as a shadow price of carbon in these next scenarios. So here you can see that we've got the different SMR technologies, so the base case and the 5 different SMR with CCS options at different rates of carbon taxes. The blue shows no carbon tax, yellow has a carbon tax of $20 per tonne of CO2, and that increases to $50 and then $100 per tonne of CO2. We compare that to different levels of hydrogen production costs. The red line is $2. Why do we compare to $2? Well, that seems to be a key target price coming out in Australia and Japan. The Japanese hydrogen strategy basically states that it hopes to be able to import hydrogen after 2030 at a cost of $2 per kilogram, which is based on the predicted price of LNG with a markup for a carbon tax. And in recent documents, that's actually been picked up as a potential target price for Australian hydrogen in the technology roadmap discussion paper. The other comparisons are presented as low-cost PEM electrolyzers. So basically, if there's a breakthrough in electrolyzer costs, how low could the production cost of hydrogen go? Those are the green dashed lines shown. You can see there that there's 2 sources, NREL from the US and CIRO from Australia. So the highest capture rate, as presented and discussed before, is always above $2 with and without a carbon tax. And this is based on the IEA GHG numbers. A $50 carbon tax means that most of the SMR with CCS options will actually be above that $2 level, which is quite a notable statement to make, especially when the target price for hydrogen could be $2. And there are some other, with no carbon tax, you can see that basically SMR is outcompeting the PEM option from CIRO as in the Australian hydrogen roadmap. Sorry. So basically, to end the discussion, we wanted to highlight the analysis that we've done in the past. So this is the conversation article that we published that talks about hydrogen and whether it's truly clean if it's not using renewables. And so you can see that based on our analysis, 4 out of the 5 SMR options would not actually be clean. How that actually gets translated into the Australian debate about what will actually get supported by the government and by industry is another question. At the moment, it's unclear what will actually be defined as clean within the Australian hydrogen strategy and the roadmap coming out of it. And this is why we wrote this article, to point out that actually some options with lower CCS capture rates will actually be quite dirty. And there you can see that we make the point that high carbon capture rates are not assured. So to conclude, Australia is one example of a potential supplier that seems to be leaning towards establishing a coal or gas-based hydrogen industry. Other countries discussing CCS options include Norway, and the interactions between Australia and Japan is relevant to our analysis. So I wanted to conclude with this example of the hydrogen energy supply chain pilot project. It's a brown coal gasification pilot that aims to produce up to 3 tons of gaseous hydrogen in 1 year. It will export that hydrogen to Japan using a liquefied hydrogen carrier that's being developed. So the ship's been launched, but without a storage tank, which is scheduled to be installed by late 2020. It's important to note that the emissions expected from this pilot project are stated to be 100 tons of CO2, and offsets are being purchased to negate these emissions. I was unable to find what capture rate the actual pilot program is aiming for, but the implication there is that it's probably not very high. So basically posing the question to conclude about whether the move towards a new carbon-intensive hydrogen industry has begun. That's an open question. It does seem that key players are not supporting renewables in the way that they could, like Germany and the EU are doing so. Key players, including Australia, seem to be leaning towards a gas-based hydrogen industry. So yes, so please get in contact with any feedback. Happy for any questions, any data on CCS capture rates or hydrogen costs, and look forward to the discussion as it rolls on during the conference. Thank you very much.